Hey there, this is the first lesson in Chapter 4 for my MIAP students in grade 10. And our first lesson is going to just focus on some stuff that hopefully you already know from grade 9, with maybe just a little bit of new information to go with it. First of all, we need to define what we mean when we talk about numbers. So hopefully everybody remembers this. This for sure you talked about in grade 9, probably in grade 8 too. Natural numbers. Here's the definition. The natural numbers is the set of all counting numbers. So we usually denote that set with the letter n, and we'd say n is equal to 1, 2, 3, 4, and of course you could count forever. This is an infinite set. Whole numbers isn't a whole lot different. It's the set of all counting numbers including 0. So we use capital W to represent the whole number set, and then 0, 1, 2, 3, 4, ... And there might be people going, well, wait a minute, don't you need 0 to count with? And the actual reality is no, that you don't. If you think about it, for example, Roman numerals go I. They didn't need a symbol for 0, and they didn't need it when they got to 10 or 100 or 1,000, because they didn't use 0 as a placeholder, so they didn't actually have 0 as a number in their counting system. But we do use zeros, not just as placeholders, but as an actual placeholder that means no value. So we call that whole numbers. Integers is defined as the set of all numbers that can be written without a fractional component. And it's the first, actually, it's not an I. The actual symbol for it is a capital Z, and sometimes people put an extra line through it like that. That tells you right away that it is the set of all numbers that we call integers. And the set of all numbers we call integers is the first set that goes forever in both directions. So ... from this direction, -3, -2, -1, 0, 1, 2, ... right? It goes forever positive and forever negative. But notice they're still whole amounts. -1/2 is not an integer. 2/3 is not an integer. Integers still have to be whole amounts. So you could think of integers as the positive and negative versions of the whole numbers. Next, you have rational numbers, and this is where it gets a little more complicated. Rational numbers is the set of all numbers that can be expressed as the quotient of two integers. This includes all terminating and repeating decimals. So rational numbers, which has the symbol Q, and again, sometimes people put an extra line in it like that, and that means the set that we call rational numbers, is, and this one, I can't actually put them in order and show you all of them at once. And how about I'll just give you some examples. So that'd be the set that includes things like 1/2, 0.3, 0.7 repeating, 1.9. I don't have any negatives in here. -2.185, and I'll just say etc. Right? So you might be thinking, well, doesn't that include everything? And the answer to that is no, and you were supposed to learn this back in grade 9. There's actually an even bigger set, and I'll explain what I mean by that in a minute, called irrational numbers. Irrational numbers that are numbers, and this doesn't fit in here very good, so I have to write small. Irrational numbers are numbers that exist on a number line which can't be represented by a fraction. So, and again, fraction means quotient of two integers. When I'll give you some examples of irrational numbers. The symbol for irrational numbers is Q with a line over it. Sometimes people also use I for irrational number. And irrational numbers is, for example, the famous one, of course, is pi. Pi is an irrational number. You probably have seen it before on, let's get a calculator up here, as 3.14159.265. That's, by the way, where I have it memorized too. I'm not one of those people that has like 100 decimal places of pi memorized. I've never quite understood the attraction of doing that. But there you go. Now, I've had people who are students in the past who have said, well, wait a minute, I thought that it can't be a fraction. I thought that 22/7 was pi. And the answer to that is, well, no, it isn't. It's close. Let me show you. See, the fact that this is a fraction means that this decimal representation won't do the same thing that this decimal representation does. The actual decimal representation of pi can't ever terminate and it can't ever repeat. There is no end to this decimal, and there's no place where it'll just start over and repeat the same digits in the same order. 22/7, of course, will do that. In fact, 22/7, if I just show you here, you can compare them. 22/7 is 3.14. Notice it right away, right there at the 2. It's, or sorry, 3.142857, and pi. Let's see. Let's get pi back on the screen here. Where are you, pi? Pi. There we go. So notice that 22/7 right here at the 2 is different than pi. It's really only the same number up to the hundredths place. By the time you're at the thousandths place, it isn't the same number, and it can't be the same number because, again, as ugly as this looks here for 22/7, it is repeating. 142857 is the repeating pattern for 1/7, and that's what 22/7 is, right? It's actually 3 and 1/7, so it's 3 and 0.142857 repeating. Pi can't do that. There's no place in the decimal where eventually you can just put a line over it and say it's repeating. It doesn't work that way. Now, why doesn't it work that way? Well, we'll get into that later. But first, some other famous irrational numbers would be things like, for example, E is a very famous irrational number. You learn all about it in grade 12. It's 2.718 and forever. Another very famous one, and we'll talk about this one in some detail, is the square root of 2. In fact, the square root of any non-perfect square will always be irrational. And then, of course, ... because, again, like I said, there's actually more. The irrational numbers actually is infinite, and it's actually a larger infinity than rational numbers is. And if that's a weird statement for you, or if maybe you've heard that statement before, we'll tell you a story about that. But before we go on any further, let's make sure we understand that even irrational numbers are on the number line somewhere. So that means that all of the above, the set of all numbers that contains all of the above, is what we call real numbers. And real numbers usually is an R with an extra line through it. And so everything here that we've talked about today is a real number. And this diagram, which you should have seen back in grade 9, shows their relationship. See, anything that is a natural number, this is a Venn diagram, by the way, anything that is a natural number is a whole number. And anything that's a whole number is an integer, and anything that is an integer is a rational number. So you can think of all the sets of numbers, and then anything that is not rational but is irrational still fits in the real numbers. You can think of this relationship, if you like a set of nesting dolls. Like these little guys here, right? The Ukrainian matryoshka dolls. If you've never seen one of these before, the way they work is they actually open up and the little one fits inside the bigger one, fits inside the bigger one, fits inside the bigger one, until you get, all 7 of them or whatever. So that's the way I've always thought of numbers. Oops, that's what I want to go to. Here we go. There. I've always thought of numbers like this set fits inside of this set, fits inside of this set, fits inside of this set. But all of these sets are infinite. And here's what's interesting. Everything from here to here, natural numbers, whole numbers, integers, rational numbers, is what we call countably. Oops, I can't spell countably. Maybe I've misspelled this. If I've misspelled countably, let me know. Countably infinite. These guys here are sort of different. They are not countably infinite. Oh man, I can't spell today. Infinite. There we go. So there we go. There's kind of a difference. These guys here, in other words, if I had infinite time, infinite pencils, and an infinite piece of paper, I could start counting 1, 2, 3, 4, 5, and if I could count forever, I would count every natural number. If I keep going, I won't miss any. Same thing with whole numbers, 0, 1, 2, 3 to infinity. Same thing with integers. I just have to count in 2 different directions. If there's people going, oh, well, that's cheating, that's not really counting if you got to go in 2 different directions, I'll say to you, okay, well, that's fine. Then I'll do this. I'll say that I can go 0, 1, -1, 2, -2, 3, -3. And again, if I had infinite time and infinite paper and infinite pencils, I wouldn't miss any integers. I'd count them all to infinity. Rational numbers, this is kind of mind-blowing, but it's also countable. This tends to blow people's minds. Here's what I mean by that. In fact, here's an interesting story. Back around, I think it was about 2012, 2013, a book was written by an author named Glenn or something, John Green. I think it was John Green. And it was called The Fault in Our Stars. It is a book aimed at young adults, aimed at tweens and teenagers. The main story involves a young boy dying of cancer, and it was really popular. The movie that came out a couple years after it was written was also really, really popular here. In fact, I remember kids walking around with these t-shirts a few years ago. And there's the quote: some infinities are bigger than others, or some infinities are bigger than other infinities. So what does that mean? Well, in the context of the book, what this character was trying to say, I actually looked up the quote. I thought we'd look it up and talk about it here a bit. Here's the quote from the actual book. There are infinite numbers between 0 and 1. There's decimal 1 and decimal 12, or decimal 1, 2, and decimal 1, 1, 2. And an infinite collection of others. Of course, there's a bigger infinite set of numbers between 0 and 2, or between 0 and a million. Some infinities are bigger than other infinities. I cannot tell you how grateful I am over our little infinity. You gave me forever within the numbered days, and I'm grateful. So this is a character who is dying, trying to console their friend that just because our time was short doesn't mean it wasn't great, and that some infinities are bigger than others. But you could think of our time as an infinite collection of moments. The only problem I have with this, I hate to rain on this deep, deep sentiment, but it's mathematically quite false. The actual infinity between 0 and 1 is the same size as the infinity between 0 and 2. Just like the infinity of natural numbers is the same size as the infinity of whole numbers. You've played that game when you were little. Infinity plus 1 is still infinity. Just because I added a 0, one more number, that's still the same sized infinity. This infinity is still the same size as that infinity. And believe it or not, this is hard to get your head around, but this infinity is still the same size. How can that be possible when, if you look at a number line, it seems like this quote's got a point here. If I go between 0 and 1, I could have, well, there's a half and a quarter and a third and a sixth and a tenth and a hundredth and a billionth. They all fit between here and here. And any 2 points on this number line, I could find you an infinity of fractions between them. So how can the infinity of fractions be the same size between 0 and 1 or 0 and 2? Well, I'm here to tell you that the infinity of fractions is the same size as the infinity of integers. It's the same size as the infinity of 0 to infinity of whole numbers, or to 1 to infinity of natural numbers. And to kind of show you that it's true, I'm gonna actually send you to a really neat video about that. It's got animation and everything. But first I'll prove to you that, you know what? Just like I could count from 0 to infinity in whole numbers, or I could count all the integers as long as I, put them in a slightly different order, I can actually count every fraction too. So first of all, keep in mind that anything that I wrote here as a decimal is in fact a fraction, right? 7 repeating is 7/9. 0.3 is 3/10. 1.9 is 1 9/10, or if you like, 19/10. Everything here is an integer a over an integer b, where b isn't 0. So all of those things can be represented as a number over a number. And if I were to take a grid like that, and I start putting fractions on that grid. Now, I'm going to put down the fractions in a very, very specific way. I am going to write my numerators will be 1 and 1 and 1. This row, the numerator will always be 1. In this row, the numerator will always be 2. In this row, the numerator will always be 3. And my denominators will, let's see, hang on. I want to make sure I do this the same way as the picture I was just going to show you. Yeah, numerators are always 1, numerators are always 2, numerators are... Okay, got it. Okay, so just to make sure that I'm doing this the same way as the picture so that I don't confuse you when I show you the picture. Numerators are always 3, because you could actually do it the other way. It doesn't matter if the numerators go up or down. Numerators are always 3. And then my denominators are going to actually count. So they're going to count down the other way. And again, here I'll just show you kind of what that looks like in the big. So my denominators are also going to count. My denominators are going to count like normal numbers. So this will be 1, 2, 3, 4, 5, 6. And again, this will just keep going. And this will be 1, 2, 3, 4, 5, 6. This will keep going. And this will, of course, be 1, 2, 3, 4, 5, 6. Now, I can keep this going. Of course, this would be then my 4 row for numerator, my 5 row, and again, for 1. Oops, that's supposed to be a 4. 4 over 2, 4 over 3, 4 over 4, 4 over 5, 4 over 6. And all of these rows go forever, and this column, of course, all these columns go forever as well. And if you're looking at that going, how does that actually list every fraction? Because first of all, it's not in order. Well, can I point out to you that if I had to make a list, I couldn't put these in order either, really. So this list isn't going from smallest to biggest, but if you were to take that list and then follow it in that direction, go down, then up, over, down, down, across, up, basically count the diagonals. So think about the path that you're taking here. 1 over 1, 2 over 1. That's it. There can't be any more over 1s until you get to 3. So 1 over 1, 2 over 1, 1 over 2, 1 over 3, 2 over 2, 3 over 1, 4 over 1. If you keep going like this, the diagonals, of course, are getting bigger and bigger forever, but you'd never miss a single fraction. Somewhere in here would be 27 over 13. Somewhere in here would be 31 over 174. Every single possible fraction would be in here, and you'd be able to hit them all by just following that direction. Follow this line of diagonals. I think I just drew that diagonal badly, but you get the idea. Count diagonals and keep turning around and snaking back and forth, and you would hit every possible fraction there could ever be. Would they be in order from smallest to biggest? Heck no, not even close. In fact, it would be impossible to list them from smallest to biggest, because any two fractions you can think of, like a third and a half, there is infinity of fractions that fit between them. But all those fractions will be on this list. So if I had a big enough piece of paper, a big enough grid, and enough pencils, I could make this list for infinity. So rational numbers can be counted. So what the heck, what math lesson did this poor cancer victim kid in this book get wrong and took to their grave not knowing exactly what the actual lesson was in math? Well, some infinities are in fact bigger than other infinities, but it isn't rational numbers like they're talking about. It's the irrational numbers. Irrational numbers are not a countable infinity. Let me kind of try to show you why. I'm going to just stick to irrational numbers that have nothing but digits 0 and 1 in them. How about my first one? And again, I'm not listing them in smallest to biggest or any particular order because I can't. I couldn't do that for rationals either. How about I'll just say the first one's nothing but 1s. I know that's actually a rational number, but maybe there's a 0 in there somewhere along the line. I'm going to stick to two different digits, 0 and 1. This one will be 0.00000. I know that's probably, again, that's a rational number. It's just 0. Well, maybe somewhere way down the line, 10 billion places over, there's a 1 or something like that. The rest of the numbers, how about I just do them by, I flip a coin. So I flip a coin and I get heads, then tails, then heads, heads, tails, 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 heads, heads, tails. And then do the same thing. And then I'll go, okay, again, this one's heads, tails, heads, heads, tails, heads, 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 tails. Now you're probably going, well, wait a minute. It's possible you get two numbers the same. You know what? Eventually, there's no way that this would be the same as the one above it exactly. I could keep this list going forever, and eventually, again, if I had infinite paper, infinite pencil, and the infinite patience to keep flipping a coin for each number infinitely, I should be able to make every possible combination of infinity of zeros and ones. They should all show up at some point. So here's the problem with this. No matter how big I make this list, I can make you a number that isn't on it. That's why I can't count irrational numbers infinitely. If there's no repeating pattern to these decimals, they're just random, there is no way to make a list that wouldn't include, or that would not be excluding another number I could make for you. In fact, here, I'll even show you how I do it. I will take the diagonals again. So I'll take this digit, this digit, this digit, this digit, and I'll just, whatever this is, I'll write the opposite of it. So the 1 is a 0, the 0 is a 1, this 1 is a 0, this 0 is a 1, and I could keep doing that forever. And you know what? I know that this number can't be on the list already somewhere. You're probably going, well, it's probably just down there somewhere. No, it can't be, because notice, it's different. It can't be that number. It can't be this row's number. It can't be that row's number. And as I make this number longer and longer, I know it can't be on any of the rows above it. So, because of that little proof that a German mathematician named Gregor Kenter came up with in the late 1800s, I think, it is impossible to make a countable list of irrational numbers. So, in fact, this infinity is bigger than that infinity. All these infinities are the same size, but that one's bigger. And since real numbers includes those ones, real numbers is a bigger infinity than all these infinities. And that's actually what this diagram's trying to say. If you're wondering why they didn't put a big circle around this and why they kind of left this as the zone, they're actually trying to show you, how come they don't put a circle around this one? They're actually trying to show you in this diagram, and they didn't tell you this in grade 9. I bet you didn't hear this story in grade 9. That this infinity is a closed infinity. I know that sounds weird. What do you mean a closed infinity? You're not going to count to the end, but it is a countable infinity. So is that one, so is that one, so is that one. This one isn't. So this entire page of real numbers isn't closed either. That's why they don't make a circle. A circle on a Venn diagram means closed or countable. So, bet you didn't hear that in grade 9. Let's do a couple of examples and send you on your way. All right. Determine whether a number, each umber, I think this should be number. Determine whether each umber is rational or irrational. Negative 15. Well, you know what? I could write that as negative 15 over 1. That's an integer over an integer rational. Oops, that's real. I meant to say Q. My bad. Q. Rational. 1.21. Well, that's 1 and 21 hundredths. And that's 121 hundredths. That's a fraction. Definitely rational. Square root of 100. Now, here's where we have to know our perfect squares. Is 100 a perfect square? Yes, it is. It's 10. So that's definitely rational. 6/11. It's a fraction over, it's a true fraction. It's a rational over a rational, or better said, it's an integer over an integer. So, yep, it's rational. 49/16. Is that a perfect square? And the answer is yes, it is, because the square root of 49 is 7, and the square root of 16 is 4. So that is definitely rational. Finally, the square root of 18. Well, let's see. Is 18 a perfect square? No. The square root of 16 is 4, and the next perfect square is way up at 25. So that is definitely not a perfect square. So this would be one of those decimals that never ends, never repeats. It is irrational. And just to double check on a calculator, let's see. Let's erase that guy. If we were to square, oops, that's not what I want. If we were to, where's second function on here? Oh, there it is. It's right in front of me. If we were to square root 18. Oh, wait a minute. This is the kind of calculator I have to have it on the screen first. If we were to square root 18, there we go. 4.242640687. See any repeating pattern in there? Nope, me neither. So again, you were supposed to talk about this stuff in grade 9, so hopefully that makes sense to you. That one's irrational. You can only get a rational number when you square root perfect squares like E or C. All right, example 2. Use a number line to order the following numbers. Okay, so the square root of 9 is just 3, so that's easy. So this is just, there's your square root of 9. Negative 5 halves, well, that's easy. That is just, I could call that negative 2 and a half. So negative 2 and another half. So there we go. There's negative 5 halves there. And the cube root of 28, don't know. How about 2.3 repeating? Well, that's easier said as negative 2 and a third. Now, hang on a sec. What do you think? Is negative 2 and a third on this side or on that side of negative 2 and a half? Well, remember that you're counting on the negative side. You're counting from right to left. So that's negative 1, negative 2, negative 2 and a tenth, negative 2 and a sixth, negative 2 and a fifth. This would be negative 2 and a third. So that one's there, and that one's there. So negative 2.3 repeating. By the way, there's no difference between 3 repeating and 3 repeating. Okay, so that's a third of the way toward negative 3. Now the two that I kind of skipped over. Is 23 a perfect square? Well, the square root of 23, the square root of 16 is 20, and the square root of 25 is, what? Let me put that again, sorry. Square root of 16 is 4 is what I meant to say, sorry. Brain cramp. Square root of 25 is 5. So I know that the square root of 23 is somewhere between 4 and 5. So in grade 8, I believe, you were supposed to learn how to estimate what that is. Now, you can kind of just do kind of a ballpark. 23 is closer to 25 than 16, so it's going to be past 0.5. So it's going to be around 4 point, I don't know, maybe 0.8 or something. If you wanted to, you could even kind of give me something like a fractional estimate by saying, okay, from 16 to 25 is 9 things, and 23 from 16 to 23 is 7 things. So you could actually maybe say it's around 4 and 7/9. Now, why doesn't that like, I used some pretty good logic there, right? I mean, 16 to 25 is 9 steps, 16 to 23 is 7 of those steps. Why isn't the 23 square rooted exactly 4 and 7/9? Well, it's because this square root scale to go from one to the next isn't linear. It's not going to land exactly on 0.7 repeating. In fact, it's going to be close. Here, let's get a calculator up again. The square root of 23 is 4.7 and then 9. So I'm off by 2/100ths. And then again, notice there's no repeating pattern to that. So it's around 4 and 7/9. So that's about here and 7/9 of the way. Kind of eyeballing that. But there we go. There's my root 23. All right. Let's try to estimate and then check with our calculator to see how good we can do with the cube root of 28. Well, what are my perfect cubes? 1 cubed is 1, 2 cubed is 8, 3 cubed is 27. Aha! The cube root of 27 is 3. The next perfect cube is way up at 64. So I know it's 3 point something, and it's way closer to 3. So I'm going to say it's like 3.1, maybe 3.05 even. But I'm going to say it's approximately 3.1. Let's see, how close am I at the guess of 3.1? So 3.1, and on your calculator, go second function cube root. Some calculators cube root's its own button. You might have to look around for it. And there you go. So I said, oh wait, sorry, it wasn't 23, it was 28. Sorry. Let's try that again. 28 second function cube root. And there we go. Like I said, it was 3.0. I guess 3.05. I was off by 2/100ths again. So it's 3.03, which is going to be really close. That'd be so close to here, you'd have a hard time telling them apart. And so that would be my cube root of 28. So I'll give you a couple of homework questions, not a lot, because I know some people are still finishing the test. And I'll give you a couple of homework questions that you can kind of practice knowing whether or not you've got a rational or an irrational number. It's pretty easy stuff. This is a nice little lesson where we got to talk about some fun stuff. I also have a video I want you to watch. I'll put a link to it on the blog here right after this video. And one last thing before we go here. I wanted to show people, if they're looking at my blog, go to the blog here. Don't freak. If you're one of those people that's fallen behind and you're still catching up on some chapter 6 and 7 stuff, you're going to go, oh no, what happened to all the updates before May the 25th? They're still there. I just felt bad for my classes after you guys who had to scroll through like a month of your assignments and things. So I just put them at the end. And if you scroll past my slot 6 class, it starts over again where it says 2019-2020 archive old posts. And then again, my first class in the morning goes first. And then this is everything right back to the beginning of the course. You're next, right? So starting, here we go, slot 3. So I even put all the textbook stuff up at the top. And then there you go. There's last Tuesday's update and last Friday and all that stuff. So if you're still catching up on chapter 7 and chapter 6 stuff, I didn't take my lesson links away. They're still here. You just have to search for them. Depending on how your browser works, some browsers don't stick the next update of the blog after it. So you can find it if you just look on the right-hand side. Like everybody, when they first go to my blog, it should look like this. You should see the title, Mr. K's FRC Math Blog. And if you look, Blog Archive, right here, Archive Old Posts will take you directly to the old posts. And then you can just scroll down again and find all the stuff that I put from chapters 6 and 7. Okay? So it didn't go anywhere. You don't have to message me going, oh no, I was trying to catch up on stuff and you took it away. No, I didn't. It's all still here. I'm kind of a hoarder when it comes to my files. I don't make I never delete them. I just put them in archives so that they're there in case I ever want to see, hey, what was I doing on May the 19th of 2020? Okay, so just thought I'd let people know that. Otherwise, that's about it. Enjoy the assignment. Thanks for watching.